We will start the supervised homework session of our course, Advanced Quantum Mechanics. We will discuss the homework package number 3. I shall remind you that the deadline for this package is, I believe in about a week, on coming Sunday, late Sunday evening. And we proceed along the rules which I put at the whiteboard. Let me shortly go through this. I will explain the formulation of the problem, perhaps giving some hints on how to solve it, how to proceed. And yeah, I didn't put it. You can put your question to the chat for everyone at this moment. Right, then we will devote some time to discussion or homework on individual basis. How do we proceed? You raise your hand in Zoom. There is a special button for this. Then an instructor contacts you in private chat. There are hopefully 4 of us. Yes, there are 4 of us, and we will contact you in private chat, and we can discuss your question. If question is interesting to everybody, then instructor kind of speaks up, discuss it with everybody. Usually it happens if an instructor has repeating questions from the audience. Very well, so let us proceed. Let me stop the share first. And I need to find the first problem of the package, which is, let us see. No, not this one. I shall start with homework problem 6. Okay. All problems on this home package, in contrast to previous problems, they deal with transitions, with emission, energy loss in different setups. All right. In first 2 packages, we mostly concentrated on second order corrections to energies. Now we do transitions. But in fact, there's much similarity between computation of second order correction and transition. What the similarity is? In both cases, we need a square of a matrix element between 2 states. If you talk about transition, the initial and final states, they have to have the same energy. And for second order corrections, those are virtual states. They don't have to have the same energy. Moreover, if they have the same energy, you have a problem. Why? Because there's a denominator in expression for second order perturbation correction. There is a denominator, which is the difference of energies. So it would blow up if energies are the same. All right. Sure. And as in computation of second order correction, we need to know, and this is always one of the first questions, explicit or implicit. we need to know the states we are dealing with, either virtual states for second order correction or final states for a transition. Right, these states are obtained by applying elements of the perturbation Hamiltonian to an initial state, to ground state, or to initial state. Don't apply the whole Hamiltonian, apply elements. Just combinations of creation relation operator, which enters here. Good, but let me concentrate on problem number 6. So we consider an electron in quasi one-dimensional circular dot. The confining potential in this case is 0 near some thin radius, and yeah, otherwise it is infinite. Right. This might sound fancy, but it's not something to think deep about this. In fact, we want you to deal with very simple question, very simple notion of the levels. We will discuss a bit further. So what is the task? We study emission of light from the excited states in the dot. Right. Validity of dipole approximation is assumed. It is the same as in atoms. What does it mean? It means that interaction of the electron with radiation field reads as follows. It's a dipole moment times electric field. Dipole moment is made of electrons in the dot, while electric field, as we discussed, is an operator in terms of creation and annihilation operators of electromagnetic field. So its explicit form is given. It contains ugly square roots, which I discussed. Right, then there is another hint coming. It's a choice of polarizations for this slide. In principle, both polarizations can occur during the transition, and the choice of polarizations is basically the same as in the lectures or in the book. It is written somehow. Okay, there's at least one typo here, but I guess you understand that this. So there are two vectors z perpendicular to the dot and vector of propagation of an emitted photon. All right, they form a plane. And first polarization vector is perpendicular to this plane, right? Well, eventually it's not a big secret that in this case, the corresponding matrix element will be 0 because polarization vector is, I'm not actually very sure what is the direction of dipole moment. It's up to you to determine it. Right, in this case, if there is a dipole moment in that direction, then there is no matrix element. The vector is just perpendicular. Okay, and the second polarization vector is perpendicular to K. Yeah, it has to be. And it is in the same plane as vector Z. Good, so perhaps it's not kind of ideally written here, but in fact it is a useful hint which will simplify your calculations. And other, let's see, it's again something with my chat. Is there a question in the chat? No. Yes, yes, Baron. The question is it correct that both vectors of polarization E1 and 2 perpendicular to K? Yes, and it has to be because we are talking about real light. In real light, there's no polarization in the direction of propagation. Good. So more questions about this point? No. All right. Then we go point by point. What are the tasks? To remind, each task is 5 score points. The last task is a bonus question. And to warm up, we find energy levels and eigenfunctions of the electron in the dot. Right. What we expect from you is just to write simple one-dimensional Hamiltonian. For coordinate phi, it means that just kind of electron just circulates and its coordinate is phi, its phase. Right, the wave function must be periodic in this coordinate phi. And well, it's also not a big secret that eigenfunctions in this case will be plane waves in phi, will be exponents of phi. And they will be quantized because they are periodic. Fine. Hope that's enough. If it's not enough, please put questions. Right. Then one needs to find matrix elements of dipole moment between the states. In fact, calculation, as we remember, consists of two: computation of this matrix elements of D and computation of matrix elements of the field. Right. And one needs to find these matrix elements of dipole moment between the states. So in principle, there are all three components available. But okay, to give another hint, we have electron which goes in the dot, so it says in XY plane, right? So I personally don't expect any Z component. All right. Good. Selection rule needs to be demonstrated. Right, then there is another point, point C. Without computing the transition rate explicitly, determine the angular dependence and the ratio of photon numbers emitted with polarizations 1, 2. This comes from comparison of matrix elements of dipole moment. So one doesn't have to deal with the density of photons yet. It comes from the analysis of matrix element of dipole moments between the states with polarization vector taken into account. Right, only after that, after all these exercises, there's a central point. One needs to compute the total decay rate, actually from an arbitrary state M. But since state M can only decay to kind of one below, then this is not a big problem. There's only one final state. Sorry, there's infinitely many finite states, but because there are all possible wave vectors of the photon involved. But in any case, the dot in final state is just in state M minus 1. Fine. Nothing in the chat yet, if I see it correctly. Perhaps I need to arrange my screen differently. Good. And there's a bonus question. Let me also outline bonus question, but yeah, I remind that we don't actually support bonus questions much. It's up to your creativity. If you answer correctly, you got score points. If you don't, you don't. Right. So, but yeah, in this case, the bonus question is to make you think physically about the situation, right? So just to complicate situation a bit, electron is excited to the fourth excited state, and then it first go to third, second, first, right, and it emits photons with different energy. It emits it with different rates, and yeah, one needs to compute the resulting emission spectrum, which has several discrete energies, and thus relative intensity of the emission. Well, that comes about of the total decay rate you have computed in previous exercise. Very good, sir. I think I explained everything in the formulation. Please look at it again. Problem number 6. Is there any questions concerning formulation? Please put it to the chat right now. Oh yeah, is there a dipole moment of a vector in xi here, or do we only use one component? Dipole moment is a vector. So electric field also a vector. So in principle, we need to use all three components. Right. So dipole moment is if it is, I don't quite see if your question implies it, but the dipole moment is indeed in XY plane. Because, yeah, so the electron is confined in a circle, which is in XY plane. Good. So now we go to next stage. So if you have questions concerning homework package, please raise your hand, and an instructor will contact you in private chat. And I will stop my share. Yeah, it is convenient to see the chat. I will also stop recording. I will record only my explanations. Problem number 7. First of all, you are already familiar with the setup. That setup is identical to that of problem number 5. We consider an impurity in a metal, and that is potentially magnetic in case when it's energetically favorable to have only a single electron at this molecule. Right, so basically all Hamiltonians are copied from problem 5. There's impurity, and this is characterized by level energy and also interaction energy. Right, the Hamiltonian for electrons in the metal, it's all fine. The ground state of non-interacting Fermi gas, all electrons are filled up to energy, which is Fermi energy. Right, then there is a mixing operator, which connects localized level with operator D and the electrons level. Right, coupling energy, it is normalized to the energy dependent of density of states. And right, perhaps it was not that explicit, no, it is explicit. We also assume that all energy differences involved are much smaller than Fermi energy. So in this case, we can neglect the energy dependence of density of states. We can assume it's constant, and then there's a very nice cancellation of this density of states. So all answers would be expressed in terms of gamma recon. Good, as usual, first questions are simple. They don't require much calculation, but you have to figure out what is the problem about. So first, neglecting the mixing, how many states are at the impurity, give the energies of the states. Something which you have already solved in problem 5. States, they differ in electron charge, 0, 1, or 2. Right, then again, we consider the energy differences and some which are required to add or remove an electron, and we figure out which state is a ground state. And now the settings are different from problem 5. Eventually, we consider the situation when the ground state is corresponds to no electron at the impurity state. Such things happen. So we need to figure out at which energies this happens. Right. Then we are coming to the main question. We consider the transitions from a certain state, which is double occupied impurity state. And there are two situations. Situation A, in this case, the impurity will lose electron one by one. First, it goes to state 1 as impurity and emits an electron to a metal. And then this state 1 on impurity may also go off of the impurity. But that depends on energy balance. If the energy of one electron state appears to be too high, that cannot happen. Then situation B takes place. Right? And in this case, the decay process is somehow complex. It will involve two electrons. Right? But we are not there yet on computing. At the moment, we just need to understand the conditions at which both situations are realized. Compute energies. Right. Situation A is simple situation, so we can immediately address it in point D. Right, initial and final states for the first and the second decay process. That's not very complex. Initial state for the first process, double occupation, final state, occupation 1. For second stage, initial state is occupation 1, final state occupation 0. And in those final states, we have an electron which goes from the impurity with a certain wave vector. To sum up overall possible wave vectors, you got the rate. There is a nice kind of check in this sentence if you understand what's going on. Good. Let's see other questions about these points. A, B, C, D. They're all simple, but again, be cautious with this simple points. They're not complex, but you need to answer correctly. Otherwise, you cannot proceed to the next point. Right. Then point E is a bit more complex. I wouldn't say it's complicated, it's just complex. We are trying to consider this complex decay process when two electrons are emitted simultaneously. For this case, it's a piece of theory, although I believe we have discussed it. Was a presentation of this sort that I don't remember, has been discussed in the book at least, and I guess it has been mentioned in the lectures. But well, in principle, it's a kind of hint, theoretical hint. So in this case, this is effective matrix element of a process which goes into stages. From initial state, it first goes to virtual state. And the energy of virtual state doesn't have to be the same as the energy of initial state. And under them, it goes to final state. And in this case, the energies of initial final state must be the same. All right. And we use this to compute the rate in the situation B, but not, since it's a homework and it's not bonus point, it's supposed to be simple. We just shortly stop off computation of this rate. We only compute the matrix element, right? For this, you need to have final states, initial state, and also virtual states. Can be several virtual states. Be aware of this. Good. What else? And the bonus point is actual expression of the transition rate. You want to have it as an integral over the energy of the spin-up electrons lost by impurity. One interesting task is to determine the energy distribution of the emitted electrons. So there will be two electrons emitted above Fermi energy, right? And the sum of the two must be the energy of this double occupied state with respect to Fermi level. But the energies can be very different. Only the sum is fixed. So it gives some energy distribution, and that is to be determined in this bonus point. Okay, this is a useful formula, but I believe that you kind of know that it's used in many parts of this course. It's how to do summation over some quantities which depend on energy only. You write it as integral over energy using this relation. Good. So I wonder if there are questions concerning formulation of problem 7. Keep losing chat. Let me stop sharing them. I see that I don't see any questions in the chat. Then I stop recording and you raise hands and we will answer your concrete questions. All right, let me outline the formulation of problem number 8. In fact, it is about dissipative quantum mechanics, about transitions in the presence of dissipation, although in a rather simple context. It is simple, but yeah, a bit tricky. One has to read it carefully and understand what is going on. First of all, there is a qubit. A flux qubit is a small superconducting loop. The two states of flux qubit corresponds to opposite directions of the current that circulates in the loop. This is perhaps if you really concentrate, if you have tunnel vision and concentrate on the solution of the problem, it's a white noise for you. Qubit is qubit. And in order to understand it, one needs to look at this at the Hamiltonian. All right, so states of split energy are mixed. The Hamiltonian is like this: splitting, mixing the Hamiltonian. Good. Then interesting things are happening. The qubit is placed inside a coil. Here's a coil. And this coil is grounded through the resistor as it's shown in this figure. Right, and this electric circuit forms an environment of the qubit to be presented, as we know, as a set of bosonic modes. Right, with this we have a Hamiltonian, which, if you remember the lectures, is a Hamiltonian of spin boson model. So there's qubit containing sigma matrices, there's environment, and this is coupling, which is written into stages. First of all, physical part. Here it shows that there's a coupling between current and flux. Mathematically, this operator of flux is expressed in terms of creation and annihilation operators of this environment. Good. And this qubit can be into states, and the state of high energy can decay. And we can, as in many problems with decay, we treat coupling Hamiltonian as a perturbation. Fermi golden rule formula is given, and we can proceed with the tasks. Right. Point A. No bosonic excitations in the initial state, so the bus is a ground state, a qubit is an excited state. What are possible final states? All right. The energy of the qubit would go to one of the bosons of the environment. So there's plenty of possible final states, and one needs to sum up overall modes to find the answer. The only point which makes it less trivial, we need to find the energies and eigenfunctions of two qubit states given by this Hamiltonian. One needs to diagonalize it, otherwise one doesn't have energies correctly. There's a question in the chat. Let's see. I guess I will stop share in the meantime. How do you know what the initial state is? It's not about knowing, it's about making. You just do something to put qubit into excited state. If you look at technical possibilities, there is, for instance, a possibility to do it with a pulse of radiation at certain frequency. Then the qubit is in excited state. Can suppose that temperature is low enough, so there are no problem with thermal excitations in the bus. That's how do I know. Does it answer your question, Frank? Can you perhaps formulate it differently? I guess we just don't understand each other. In most problems of the sort, initial state is just given, right? And in this particular problem, it's an excited state of the qubit and no bosons in the environment. The question says how to determine the initial state and possible final states. Let's see. I don't see this in question formulation. Describe the initial and all possible final states and give their energies. Describe. Right. This information which you need to set this initial state is given here. Transition rate from the upper to the lower state of the qubit at first element, and no boson excitations in the initial state. I believe that solves the problem. No, it is written that initial state is an excited state of the qubit. It's written here from the upper to the lower state of the qubit. Good. So I guess I will go further with outlining. Good. So we know these states are very common. We have looked at it in different problems, in different aspects. And now, having exercised that much, we can immediately proceed with a B. Calculate the transition matrix element and express the rate in terms of this FM. Not to forget what are FMs. Those are here. Those are constituents of operator of the magnetic flux. Fine. Then, as it's written, the goal of the further calculation is to express this rate in physical terms of resistance, inductance, current, and qubit Hamiltonian. Good. Then see, if you look attentively, in fact, we've done it in the lectures. You're requested just to repeat this computation in a simpler setup. And this relates the response function and the squares of m which we use. All right. So you can look at the lectures in the book or whatever. You can derive it yourself. Nothing is really complex. So equations are for bosonic operators. You solve it with Fourier method, time. So everything becomes function of frequency. I is function of frequency and the response phi is function of frequency, and one has to find the response function chi, proving that this is the good relation. Good. This is quantum mechanics. For point D, you need to forget quantum mechanics. Instead, one has to recall classical theory of circuits, right? And the same susceptibility can be computed if one considers current source, which is in this circuit, right? With this, one computes susceptibility, imaginary part of it, and substitutes it to the answer obtained at B. Useful formulas, right? It's Heisenberg relation and how do you call that? Cauchy formula, which will be needed to derive this. Good. Do we have questions concerning formulation of this problem? If I were you, I would, but perhaps you are already tried. I don't see any. Jesus Christ. Oh, I didn't share my screen. I apologize. In that case, I have to quickly go through all the problem again. Homework problem 8. Qubit in a small superconducting loop. Hamiltonian is given, and a bit later, one needs to compute energies and eigenfunctions of this Hamiltonian. Our environment is a set of bosonic modes. Coupling to the environment is important part. There are coefficients Fm, which we'll later express in terms of susceptibility, but not in the beginning. So first point, just figure out what are excitations, final initial state. Our second point is to compute the transition matrix elements and eventually the rate in terms of Fm. Then there is a derivation which repeats derivation from the lectures and the books. And the calculation of the response function from classical theory of circuits.